Measures of central tendency, the mean, median, and the mode. A measure of central tendency, or MCT, is a value where a set of data values tend to cluster. It represents or summarizes all observations in a data set. So one example of an MCT is the GPA, or the general passing average of a student in a semester, and most popular Philippine actress among teenagers in the year 2020. There are three MCTs: the mean, the median, and the mode. First, the mean. It is simply the summation of all values in the dataset divided by the total number of values. So, in effect, it is simply the average or the simple arithmetic mean. It is denoted by mu, the Greek letter mu. This is read as M, Y, O, O, mu. If the data are population data with big N elements and X bar. So this is an X. There's a bar above it. Therefore, it is read as X bar. If the data are sample data with small n elements. So the formulas are given here. You should know your summation notation. The mean is also obtained from a quantitative data only. So you cannot obtain or get the mean from qualitative data. It is also unique, meaning a data set has only one mean. So when you solve the mean for a data set, you can only get one mean. It is easily affected by extreme values. So when your data set has big values or small values, the mean will be affected easily. For example, you have values that are small and then there is one big value. Then it tends to pull your mean up or it becomes larger. If your data set has very small values, your mean will tend to become smaller. One property of the mean is this: the summation of xi minus the mu is equal to 0 as I goes from 1 to n. So this is for the population. Okay? The other one here is for the sample. So how do we prove this? We use some examples. It means here that when you sum all the deviations of the observations from the mean, it should be equal to 0. Suppose we have the values 3, 5, 4. These are the values of our population. So when we get the mean, we simply add 3 plus 5 plus 4. This is equal to 12 divided by 3. The answer is equal to 4. So the mu, so take note, the mu. So whenever you see this mu, this is the population mean. The mu is equal to 4. So we use this mu in this equation. Let's say xi is 3. So 3 minus 4 is equal to negative 1. 5 minus 4 is equal to positive 1. 4 minus 4 is equal to 0. Therefore, when we get the sum of these values, this should also equal to 0. Now, suppose we get a sample from this population, a sample consisting of 2 elements using SRS, or simple random sampling. Suppose we get the numbers 3 and 4 from 3, 5, 4. So we now have our sample. Is this really true? So we get the sample mean, x bar is equal to 3.5, meaning 3 plus 4 is 7 divided by 2 because our n here is equal to 2. Our n here, by the way, big N is equal to 3. So again, we do the same process. So 3 minus 3.5 is equal to negative 0.5. 4 minus 3.5, the answer is 0.5. If we add all these values, the answer would be equal to 0. So when your answer here is equal to 0, you are sure that you are computing the correct mean. Another property is this. The summation of xi minus a quantity square as I goes from 1 to big N is at minimum when a is equal to the mu or the population mean. This is for the population. Okay? And or rather the summation of xi minus a, okay, quantity square as I goes from this is small n, as I goes from small n is at minimum when a is equal to x bar. How do we prove this? So again, using the same example as before. So we have 3, 5, 4. We know that the mean is equal to 4. When we say minimum, it is smallest. The value here is smallest when your a is equal to the mean itself. So if we use the mean for this computation, so we have 3, okay, minus 4, quantity square. So we have 3 minus 4 is negative 1. You square this is equal to positive 1. 5 minus 4 is 1. You square equal to 1. 4 minus 4 is 0. You square is equal to 0. So if you add all these values, the value is equal to positive 2. Down here, take note, we have mu. This is now our a is equal to 4. Suppose we have we take another value that is smaller than the mean. So the mean is 4. We take a value a equal to 3. This is smaller than 4 because our mean is equal to 4. This is smaller than the mean. So let us try. So 3 minus 3 is 0. You square is equal to 0. 5 minus 3 is equal to 2. You square, the answer is positive 4. 4 minus 3 square, 4 minus 3, okay, a quantity square is equal to 1. And you add these values, the answer is equal to 5. Now let's say we take another value that is greater than the mean. Suppose if we have the mean is equal to 4, okay, no? And your a here is less than the mean, it's equal to 3, we try a larger number. Let's say 5. So let's see if this is really, if this is really true. So we have 3 minus 5 is equal to negative 2. You square, this is equal to positive 4. 5 minus 5 is 0. You square, it's equal to 0. 4 minus 5 is negative 1. You square is equal to positive 1. When you add these values, the answer is equal to 5. Now, the values here are 2, 5, 5. And the smallest value is 2. It happens when our a here is equal to 4. And this is in reality our mean. So, in effect, it is true whenever your a is equal to the mean itself. So this value here is really smallest when your a is equal to the mean itself. We will not try using this for our sample because it will have the same result. Let us go to the numerical examples. First, find the mean weights in kilograms of a sample of 5 students. So It is indicated here the sample of 5 students. So we have n equal to 5. Small n is equal to 5. So solution, we want to find our x bar. This is the sample mean. So we simply add all the values in our sample, divide by 5. So 56.5 plus 61.9 up to 60.5 divided by 5. The answer is 59.2 kilograms. So meaning all values tend to cluster around 59.2 kilograms. Number 2, if the sum of scores of all students is 100, this is 132 rather, 132 in a 20-item biostatistics quiz, and the mean score is equal to 12. So is this? This is 132. Then, how many students took the quiz? Solution. You are given this, the summation of xi, or the sum of the scores, as 132. And the mean is 12. The symbol now is mu. Why mu? Because of the word all students. It refers to the population. Therefore, you have to find what is the population size, or how many students all in all took the exam, okay, from the population. This is big N. So using our formula of mean, or the mu, we have mu, the summation of xi, all over big N. So algebraically, okay, you can manipulate this. Okay, the mu, the n goes up, and the mu goes down. Okay, so we substitute our values here. So we have first 132 divided by 12. The answer is 11. So meaning there are 11 students who took the exam, and the mean score is equal to 12. Up to the second MCT, the median. This is simply the middle value in an ordered set of observations, meaning it is arranged in ascending or descending order. The single value when n or small n is odd, meaning when your n is, or your sample size or population size is odd, meaning those numbers that are not divisible by 2 exactly, then it is simply the single value, single middle value. Otherwise, the mean of the two middle values when n or small n is even. This is the mean of the two middle values, denoted by mu sub d for population and x bar d for sample. The median is obtained from numerical data only, so the same as the mean. You cannot solve the median if your data are not numerical or quantitative, not quantitative. And it is also the same as the mean. It is also unique. A data set has only one median. Next is not easily affected by extreme values. This is one good characteristic of the median. It is not easily affected by extreme values. It is always available. You can always get a median, but it might not be the actual value in the data set. Numerical examples. Number 1. Find the median weight in kilograms of a sample of 5 students. The weights are given here. Okay. And we know that n is equal to 5, so we have an odd number in our data set. So, solution, always remember, arrange the values in ascending or descending order. So, we try in ascending order. So, ascending meaning from lowest to highest. So, 56.5, 57.8, 59.3, 60.5, 61.9. So, what we do is find the middle value. So we have 5. So cancel out this. So the single value at the middle is 59. Okay, 59.2. kilograms. So the median weight of the sample 5 students is 59.3 kilograms. Next, refer to number 1. Number 2, refer to number 1. Suppose Tom, the heaviest student, is replaced with Gina, who is heavier than him. What is the new median weight? So, suppose Tom, the heaviest student. So, therefore, in this data set, okay, the heaviest weight is 61.9. This refers to Tom's weight. This is Tom's weight. Tom's weight. Okay, so he is the heaviest student. He is replaced by Gina, who is heavier than him. So, if Tom is 61.9, it can be Gina's weight is larger than 61.9. What is now the new median weight? So, if Tom is removed from the group, okay, and this is replaced by Gina, who is heavier than Tom. So, therefore, this is Gina's weight now. We don't know the actual weight of Gina, but we know that this is larger than 61.9. So, therefore, what is the new median weight? So, again, we find the central value since our n is still equal to 5. It does not become 6. It is still equal to 5. So, again, the median weight is equal to 59.3 kilograms. It is a property of the median that the values or the median, okay, is not easily affected by the presence of extreme values. So if you place this with a higher number, let's say 100 kilograms, still the median is 59.3. If you replace this 56.5 by a smaller number, still the median is equal to 59.3. So the median is not easily affected by extreme values. Those values are very large or very low. Refer to number 2. Suppose Rico is added to the sample and whose weight is the lightest of them all. What is the new median weight? So, before we had, in number 2, we had n equal to 5. Okay. Now, suppose Rico daw is added to the sample. N now becomes 6. So, we have this characteristic of Rico. His weight is the lightest of them all. So, in ascending order, this is Rico's weight. Then we have 56.5, 57.8, 59.3. And then the last is Gina's weight. So, what is now the new median weight? So, first, we cancel out the last two. Then, the remaining numbers now are 57.8 and 59.3. Now, we get the mean of these values, and that is now the median of our data set. Okay, I'll give you time to answer the question. What is now the new median weight? Okay, the answer is 58.55 kilograms. Okay, so we simply added our two values here, 57.8 plus 59.3 divided by 2. So if your n is even, by the way, 6 is even, okay, we simply get the average of the two middle values. Understood? So far, so good. Let's go to the next measure of central tendency, the mode. The mode is the most frequent observation occurring in a data set, denoted by mu sub 0 for population and x bar 0 sub 0 for sample. Not unique, meaning a data set may have more than one mode, and the mode may not exist in the data set, and obtained for quantitative and qualitative data. By the way, among the three MCTs, the mode is the easiest. All you have to do is count. You don't have to solve anything. All you have to do is count. All you need to have is a clear or clear eyes. Numerical examples. Number 1, find the modal weight in kilograms of a sample of 5 students. So the weights are here. So what is now the modal weight? By the way, the modal is a is the adjective of the modal. We don't say modal weight. We don't say modal weight, but we say modal weight. So the answer is no mode exists, or mode does not exist. Why? Because if you look at the data, okay, there is no value that is higher than another value. They have the same number of frequency. So therefore you write no mode exists, or mode does not exist for this data set. Number 2, suppose Fred, who weighs 59.3 kilograms, is added to the sample. What is the new modal weight? So let's say we add Fred's weight here, 59.3. What is now the new modal weight? So in this case, we have two 59.3s. Therefore, the mode here is equal to 59.3 kilograms. Understood? Next, number 3, find the mode of the following data sets. So you're asked to find the mode of the following data sets. So we have different values here for the first data set. Okay, so let us find the most frequent value. So in this case, we have 2, negative 2. Okay, 2 appears thrice or 3 times. Therefore, the mode here is negative 2. By the way, when your data set has only one mode, in this case negative 2, this is mode for your data set, your distribution or your data values here are said to be unimodal. So unimodal distribution. Unimodal distribution. Unimodal distribution. Next, we have the values 23, 45, 24, 34, 23, 30, and so on. So let us look for the mode. Let us look at the number 23. Okay, so we have two values here. Then, let's say we use the yellow pen. Okay, 45. Okay, 24. 24, no. And then we have 34. Okay, 34. And then 34. So we have two values for 34. About 31. Okay, no. And 45. So, and 24. So they only appear once. So therefore, the modes for our data set are 23. Okay. And 34. Therefore, when your data set or distribution has two modes, the distribution is said to be bimodal, meaning bi is two, bimodal distribution. If your data set has three modes, therefore, your distribution is said to be trimodal. If your dataset has many modes, it can be said that your distribution is multimodal or polymodal distribution. Understood? Then we have the next dataset. So let us look at the values. So we have 4 4s, 4 7s, and 4 10s. What is the mode for this data set? Any guess? In this case, we have no mode exists. Why no mode? Why no mode? Because the values here, the frequencies for our values are the same. So we have 4 4s, 4 7s, and 4 10s. There is no value that exceeds one another or has higher frequency than the other. They have the same number of frequency. Therefore, there is no mode or no mode exists. For the next data set, we have 3, 3, 3, 3, 3, 3, 3. All of them are 3. So, in this case, the mode is equal to 3. This is a unimodal data set. Unimodal data set. Now, the next data set consists of the letters in the state of Mississippi. MI, SSI, SSI, PPI. So, let us look for the mode. So, M has one frequency. How about I? Let us use the blue pen. So, I, 1, 2, 3, 4. I is equal to 4. What about S? What about S? So, S, you have 1, 2, 3, 4. How about P? Oh, we only have 2. So, P, 2 only. So, therefore, our modes here are what? We have S. We have I. First, we have I. And we have S. Okay. So, this is a bimodal data set. Bimodal data set. Now, this is one characteristic of the mode that is different from the two previous MCTs. The mode can be obtained from data values that are qualitative or quantitative. Understood? Now, you may ask, if you are given a data set, what is the best MCT to use? So, this is to remind you that when your data set has extreme values or many values that are very large or very low, then you use the median, because the median is located at the center. It is not affected by the presence of extreme values. If your data set or data values are more or less the same, not too high, not too low, then you better use the mean. If you want to find what is the most frequent, let's say if you are doing surveys quantitatively or qualitatively, then you can use the mode. Let's say, who is the most famous actress according to teenagers in 2020 in the Philippines last year? So when you go to the survey, you count, okay, who answered this particular actress. Then you find the mode of your data values. Understood? I hope this helps in finding the MCTs and what to use for your data sets. Thank you.